Welcome back, students. In the last online class, we have already come to know about the metals and non-metals. And especially in the last class, we discussed the physical properties of metals and non-metals. At the same time, in the physical properties, we have differentiated. Actually, we tried to differentiate between the metals and non-metals on the basis of those physical properties. And we came to know that it is really very difficult to distinguish metals from the non-metals on the basis of their physical properties. So we told you in our last class that in the next class we shall be discussing about the chemical properties, and it is only the chemical properties which can actually help us to find out the difference between the metals and the non-metals. So let's start. Metal can be well described only on the basis of their chemical properties. So to understand those chemical properties, in this class today we shall be discussing the reactions of metals with oxygen, that is being displayed in this slide you can see. After this we shall discuss the reactions of metals with water, and then reactions of metals with acids, reactions of metals with other metal salt solutions. And then finally we will come to discuss the reactions of metals with the non-metals. So let's start the first slides, and that is the reactions of metal with oxygen. It is actually all metals which are reactive. They very quickly, or if not quickly, slowly under certain conditions can react with oxygen. We can see here almost all metals, they react with oxygen to form metal oxides. So metal plus oxygen definitely will form metal oxides. So if we see the reaction, you can say metal plus oxygen, you can see in the blue ink it is written towards the end, metal plus oxygen is metal oxide. Here we are bringing the example of potassium metal. You can see potassium is combining with oxygen 4K plus O2 and is producing potassium oxide. After balancing, it is twice KO2. So it means that potassium reacting with oxygen and producing potassium oxide, which is a metal oxide. Here potassium is a very active metal, so it reacts spontaneously with oxygen. Not only potassium, you can say sodium is another reactive metal, or we can say sodium is the most reactive metals. So sodium reacts with oxygen in normal room temperature. You need not have to do anything. Just expose a piece of sodium into air and you will see quickly oxygen will start reacting with sodium and will produce sodium oxide. The reaction is given below, 4Na plus O2, that is twice Na2O. Means sodium is reacting with oxygen and is producing sodium oxide. After sodium, the next reactive metal comes, that is potassium. And potassium, already we have discussed in the previous slide, potassium also reacts with oxygen and produces potassium oxide. Next we are saying most metals oxides which are actually producing due to the reaction of metal and oxygen, metal oxides are produced, and these metal oxides are mostly insoluble water. But there are some metal oxides which can dissolve in water. And if the metal oxides, they dissolve in water, they form alkali, and alkalis are basic in nature. Frankly speaking, metal oxides are basic. So metal oxides are basic oxides, but all metal oxides never dissolve in water. Some metal oxides dissolves in water and they form alkalis. That is to say, therefore, all alkalis are basic in nature. That is to say that all alkalis are bases, but all bases are not alkalis. For example, we can take sodium oxide Na2 and potassium oxide K2O. These are the two oxides of metal that we have discussed in the previous two slides. These two metal oxides are soluble in water and they can quickly dissolve in water to produce various alkalis. We can see the reactions there. Sodium oxide is reacting with water producing sodium hydroxide, and potassium oxide is reacting with water and producing potassium hydroxide. Here sodium hydroxide on the left hand side you can see, and potassium hydroxide, these two metallic oxides are bases. But after reacting these bases with oxygen, on the right hand side whatever is producing, that is sodium oxide or potassium oxide, these are called as alkalis. Now we can say magnesium does not react with oxygen at room temperature. Magnesium is also a metal. We have said metals react with oxygen to produce metallic oxides. But magnesium being a metal, it doesn't react with oxygen at normal condition, that is in normal temperature or at room temperature. But if you can heat magnesium, if you can heat a magnesium metal, piece of magnesium or a magnesium ribbon, but before that you need to clean the magnesium metal or magnesium ribbon. After cleaning, if we just heat the magnesium in presence of air, then it will also react with oxygen and will produce magnesium oxide. We can see the reaction twice Mg plus O2 is producing magnesium oxide. Let's come back to the next example, and it is zinc. Zinc will react with oxygen and will produce zinc oxide, and you can see the reaction twice Zn plus O2 is producing twice ZnO. Here zinc on the left hand side reacting with oxygen producing zinc oxide, ZnO, zinc oxide. Similarly, you will get another example, and that is iron. Iron fillings. You know what is fillings? Fillings means the powder. If you just cut a piece of iron with a saw, then some powder like structures will appear, and these are called as iron fillings. These iron fillings will burn in a flame of a burner, and when it burns, definitely oxygen will come and combine with it, and as a result iron and oxygen, when they will combine together in presence of heat, will produce iron oxide, that is Fe3O4, that is ferrosulfuric oxide or mixed iron oxide. Copper is another metal. It is interesting. Copper is the least reactive metal, so it doesn't burn. It doesn't burn means it doesn't burn in presence of oxygen to produce any metallic oxides. But if you can heat copper metal extremely to a high temperature, then hot copper metal will come in contact with oxygen and will form a layer of copper oxide around the metal copper, and that layer will be black in color. So we can say that copper, under certain special condition, that is hot copper, when you will bring in presence of oxygen and burn them, then a black layer of copper oxide will be formed around the metal copper. Aluminium is another metal, and it develops another layer, that is a thin layer of aluminium oxide when it is exposed to air. It means that aluminium also reacts with oxygen to produce aluminium oxide. So we have seen so far in these slides that metals are actually reacting with oxygen. Some metals are reacting spontaneously without any problem, while some other metals are reacting under certain conditions, that is you need to heat them, or extreme heating is necessary, or sometimes iron fillings. For example, in case of iron fillings were necessary. Solid piece of iron may not react quickly with oxygen, but if it is iron fillings, and if you can sprinkle those iron fillings over a burner flame, it will come in contact with oxygen and will produce mixed iron oxide, that is Fe3O4. Coming back to amphoteric oxides. Now, as I have already mentioned, metal oxides are usually basic in nature, and they, when dissolved in water, they form alkalis. But it is not always true, because some metal oxides are there, like aluminium oxide, or you can say zinc oxide, Al2O3. You can see in the screen, it is clear, Al2O3, aluminium oxide, or zinc oxide, ZnO2. They react with both acids as well as bases, and in both the times they will produce salt and water. It means that aluminium oxide and zinc oxides are the metal oxides which can behave in a similar way with the acids and with the bases. Such metal oxides which behave similar in presence of acid and in presence of bases are called as amphoteric oxides. So amphoteric oxides have the dual nature. They exhibit both acidic and basic properties. That is why aluminium oxide and zinc oxides are called as amphoteric oxide. You can see the example, aluminium oxide, it is given in red ink. You can see aluminium oxide, Al2O3. It is reacting with hydrochloric acid, 6HCl, and then it is producing aluminium chloride, which is a salt, plus 3 molecules of water. So in this reaction, we have seen aluminium is reacting with acid, producing salt and water. But in the next example, if we see same aluminium oxide, this time is reacting with sodium hydroxide. And at that time also it is producing another salt, sodium aluminate, and water molecule. So it proves that aluminum oxide is a metal oxide which is showing similar chemical reactions with acids and bases. So these metallic oxides, we are calling it as amphoteric oxides. So you can see amphoteric oxides. Amphoteric, that is, react with acid and alkalis to produce same thing, that is salts and water. For example, aluminum oxide, it is given aluminum oxide is a base. It is basic in nature. Why? You can see in the first reaction, aluminum is reacting with acid and producing salt and water. Whenever acid is producing salt and water with something, then that something must be a base. So here aluminum oxide is behaving like a base. But in the next example, if you see, aluminum oxide this time is reacting with sodium hydroxide. This is a base and result is same. It is producing salt and water. Now who produces salt and water with base? An acid. So this time aluminum oxide is behaving as an acid. So in both these chemical reactions that we can see, aluminum oxide in the first reaction is behaving like a base, but in the second reaction it is behaving like an acid. So that is why aluminum oxide is a special kind of oxide, and that is amphoteric oxide. Remember, not only aluminum oxide, zinc oxide also exhibits the similar phenomenon. Coming to see the next reaction, that is reactions of metal with water. So in the reaction of metals like potassium, sodium, etc., as I have already mentioned, they are very active metal, so they react vigorously, quickly, spontaneously with cold water. Just drop a piece of sodium in cold water, or just drop a piece of potassium metal in cold water, and just wait, and you see both the metal will start burning in presence of cold water and will produce hydrogen gas. So this is a very special thing. Why? Because this time we have seen that metal not only reacts spontaneously with oxygen, these metals like potassium and sodium can also react spontaneously with water. However, in this chemical reaction, the hydrogen gas which is produced as a result of this reaction starts burning. Why? Because a lot amount of heat is also generated in such chemical reactions. So that is why this type of chemical reactions, when sodium metal or potassium metal reacts with water, produces heat, and we call them as exothermic reaction. This we have already discussed in our second chapter. You can see the chemical reactions. Potassium metal, you can see twice K, reacting with water to H2O, producing potassium hydroxide, twice KOH plus hydrogen gas, and at the same time heat is generated. This heat will burn hydrogen gas because hydrogen is a combustible gas, and in presence of heat, hydrogen quickly burns. At the same time, sodium is also showing the same chemical reaction. You can see sodium reacting with water, producing sodium hydroxide and hydrogen and heat. So in both cases, what will happen? Heat will be generated, and the heat will definitely burn the hydrogen gas. So these exothermic reactions are to be done under some special care. Otherwise, some accidents may take place. You can see in this diagram, when a piece of sodium is dropped in water in the beaker, immediately it will catch fire. You can see in this picture. Now calcium metal is another one, and it also reacts with water, but it reacts less vigorously. It is why? It is because calcium is a bit less reactive than sodium and potassium. But the result is same. It will also generate hydrogen gas. You can see calcium reacting with water, you will produce calcium hydroxide and hydrogen gas. This time the heat generated is less, and therefore this less amount of heat will definitely not help the hydrogen to burn. So it is comparatively a safe chemical reaction. If you see now magnesium, another metal, it reacts with hot water only. We have seen sodium and potassium can react with cold water, and same thing calcium also can react with cold water. But magnesium, its reactivity is decreasing, so it cannot react with cold water. What you need? You need hot water. If you can bring hot water in presence of magnesium metal, then it will combine with the metal and will produce magnesium hydroxide, and at the same time hydrogen gas will be generated. You can see the reaction, magnesium plus water producing magnesium hydroxide plus hydrogen gas. So in the next slide we can see metals like aluminium, iron, zinc, etc. After sodium, potassium, calcium and that is magnesium, we are coming to the next metal now, aluminium, iron and zinc. They do not react either with cold water or with hot water. So what happens to them? they actually will react with steam. That is, water is to be converted to steam. That is, more heat is required. If you just can bring steam in contact with aluminium or iron or zinc, then definitely they will react with them and will produce metal oxide. This is, you can see, reaction twice aluminium reacting with 3H2O. Remember, this water is not in liquid state, it is in the gaseous state, means steam, and is producing aluminium oxide and hydrogen gas. In the next reaction, you can say iron is also reacting with 4 molecules of water, means it's steam, it is in gaseous form, producing Fe3O4 plus 4 hydrogen molecule. This Fe3O4 is mixed iron oxide or ferrous oxide. So metals like gold, silver, platinum and copper, they will never react with water in any condition. It may be cold water, it may be hot water, it may be steam, it may be hot metal of gold, silver, platinum and copper. For no reason they will react. That is, they were never going to react with water. So that is why they are also called as noble metal. Now we are coming to see reactions of metal with acids. Metals react with acids to produce salt and hydrogen gas. We have come to know these things when we have discussed acids, bases and salt, chapter number 2. We have come to know. So it is a repetition of the same thing what we have learned in second lesson. That is, what is that? Metals react with acids and they produce salt and hydrogen gas. I have given so many examples. You can see 4 examples are on the screen displayed, and all the examples we have already discussed in our previous class. So I don't want to waste time by discussing all these things. The reactions are clear, you can see it. Now, one thing we have seen that the active metals can react spontaneously with air, water, acids, etc. And less active metal will take a bit longer time, and noble metals will never react with those reagents like air, water or acids. So depending on this, we can arrange the metals on the basis of their decreasing reactivity. And that decreasing reactivity, we can see magnesium, it is the most active metal in the 4 reactions that is given in this slide. The reactions which are given in red ink, you can see. In these 4 reactions only, we are talking about 4 metals like magnesium, aluminium, zinc and iron. Here magnesium is the most reactive, aluminium comes next, zinc comes next, and iron is the least reactive metal out of those 4, amongst these 4. Copper does not react with acids, and that is why there is no chemical reaction of copper with any acids. Nitric acid, HNO3, and the reaction of nitric acid with metals. This is interesting. Why? Because hydrogen gas is never evolved when it is a metal reacts with nitric acid. We have already mentioned that metals react with acids and produce salt and hydrogen gas. But there is something special, and that is nitric acid. It doesn't produce hydrogen gas. Why? Because it oxidizes the hydrogen gas. Actually, hydrogen gas is produced during the chemical reaction, but instantly the hydrogen gas which is produced is oxidized by the nitric acid and is converted to water. That is why you will say that nitric acid, when reacts with metal, will never produce hydrogen gas. But magnesium and manganese react with dilute nitric acid. Only 2 metals you can say, manganese and magnesium. These are the only 2 metals which can react with dilute nitric acid, HNO3, and can produce hydrogen gas. And the reaction is like that. You see magnesium reacting with nitric acid, producing magnesium nitrate, and at the same time you can see hydrogen gas is produced. So we have seen here a chart, that is reactions of metal with air, water and acids. This is the chart we have already discussed, like potassium and sodium. Their reactivity with air, they burns vigorously to form oxides. Then we came to know that reaction with water, that is with cold water, they can react. And acid also, they react violently, and at the same time they produce hydrogen gas along with salt. Then we came to the next category, calcium, magnesium, aluminium, zinc and iron. These are the metals which burn with decreasing vigor down the series. Means they are also reactive but a bit less than potassium and sodium. At the same time, magnesium reacts with hot water to form magnesium hydroxide and hydrogen gas. And the same thing is also same for aluminium, zinc and iron. And finally, we have come to know that reaction of these metals with acids, in the last we can get, they react to form hydrogen gas and salt solution, but their reactivity is less, so this reaction will be a bit slow. So reaction of metals with solution of other metal salts. This is interesting. We have so far discussed reaction of metal with oxygen, reaction of metal with water, and now we are coming to discuss there is reaction of metal with acids also we have discussed, and now we are coming to see the reaction of metals with the solution of other metal salts. To understand this, let us go for this activity. You can just concentrate in this diagram. You can see there is a beaker, and in that beaker we are having two nails. You will come to know what actually is happening to these two nails. But before that, let's take a test tube. You can see on the right hand side diagram there are two test tubes. Actually, this left test tube you consider. The left hand side test tube is filled with copper sulfate solution, which is blue in color. Now we are putting an iron nail into this copper sulfate solution. So what was the nail? You can see on the left hand side. This I am talking about this nail. So this nail is a fresh nail. We are putting it into the copper sulfate solution and we are waiting for some time. After some time, what we will see if we remove the nail from the copper sulfate solution, the color of the nail will change, and color of the nail will change like this. What is that? You can see over the nail you will see a layer of copper will be there. So the nail will turn a bit brown. And what will happen in the test tube? You see, initially in the test tube there was copper sulfate solution which is blue in color, but now the color is faded. It has become almost colorless. Now the question comes, why the color of the nail changed? And the second thing, why the color of the solution in the test tube changes? The answer is here. Iron, you can see, iron nail. You dropped it in copper sulfate solution. So reaction took place between iron and copper sulfate, and it produced copper metal and ferrous sulfate solution. Here, first there was a solution in the container in the test tube, copper sulfate, and its color is blue. But after the reaction is finished, the solution has turned to be ferrous sulfate, not copper sulfate. Remember, only copper sulfate is blue in color, but ferrous sulfate is colorless or pale green in color. That is why the blue color of the test tube disappeared and the color in the test tube almost became faded. But why there was a brown color around the nail? The reason is, before the reaction started, you put there a nail, but after the reaction, what has happened? As a result of displacement, copper is produced, and that copper metal which is produced in the solution will get deposited on the metal, iron metal, and as a result, the color of the iron nail has turned out to be brown. So this is actually a displacement reaction, and here we have seen that a more active metal, which is one more active in this particular reaction. We are talking about two metals, iron and copper. Out of these two, iron is more active, so it has displaced copper from copper sulfate solution. So what we have come, frankly speaking, that a more active metal will displace a less active metal from its salt solution. So this is how metals react with the salt solutions. Now, reaction of metals with non-metals. Metals react with oxygen, they can react with water, they can react with acid, they can react with base, they can even react with the salt solution of other metals. So last but not least, we have come to know that reactions of metal is possible with even non-metals. So let us look at the electronic configuration of some metals and non-metals first. It will help us to understand that is actually the reactivity of different elements in the formation of different compounds. And we will see this is the chart where you can find out the electronic configuration of some metals. Electronic configurations already you have come to know in your class 9 standard. So I hope these things are not difficult for you. So there is electronic configuration of sodium. You can say in the K cell there is 2 electron, in L cell 8 electrons, and an M shell 1 electron. So its electronic configuration is 281. Magnesium is 282, aluminum 283, potassium 2881, calcium 2882. Now see non-metals like nitrogen, this electronic configuration is 25. 2 electrons are there in the K shell, and in the L cell there are 5 electrons. Similarly, oxygen 26, fluorine 27, phosphorus you can see 285, sulfur 286, and chlorine 287. So these are the electronic configuration of some metals and non-metals. Now what? Sodium is a silver colored metal, and that reacts so violently with water that flames are produced due to the formation of hydrogen gas. We have discussed it. So what is sodium? Sodium is a very active metal and its color is silver color. If you just drop it in water, then it will catch fire. If you just expose it to air, it will quickly react. Such a reactive metal sodium is. Now come back to chlorine. Chlorine is what? It has a greenish color. So this gas will appear a bit green in color. And it is very poisonous gas. Extremely poisonous. Chlorine. It is so poisonous that it can even kill the disease-causing germs that remain mixed in water. So that's why we mix bleaching powder in water. We have discussed in our second chapter. Because bleaching powder releases chlorine gas, and this chlorine can kill the disease-causing germs present in water. So we are talking about 2 elements, sodium and chlorine. Sodium, very reactive, quickly burns in presence of water. Chlorine, we have seen a green colored gas which is poisonous. But when this sodium and chlorine, one metal sodium and one non-metal chlorine, combine together, they react with each other and they form a very simple thing, ordinary thing, and very necessary thing. And what is it? It is a common salt. That is table salt. Common salt or table salt. But the question is how this sodium metal reacts with chlorine. We need to understand it. So sodium, it has electronic configuration 281, we know. And at the same time, chlorine has electronic configuration 287. In class 9 standard and even in class 8 standard, you have come to know about octet rule. And as per the rule, what you have come to know, that all elements try to maintain 8 electrons in their outermost orbit. But what is the number of electron in the outermost orbit of sodium? You see this? It is only 1. So it's unstable. Similarly, in case of chlorine, it is 7. Both these elements, sodium and chlorine, has to maintain 8 electrons in the last orbit, outermost orbit. Sodium has 1, chlorine has 7. But one thing can be done. If the last electron, the number last, that is in the L shell, there is only 1 electron. If that electron from sodium is removed and this electron is added to chlorine in the 3rd orbit, so what will happen? Sodium's electronic configuration will change to 28 and chlorine's electronic configuration also will change to 288, and they will fulfill octet rule. And as a result, what will happen? Sodium will quickly get changed to sodium positive ion because it is losing 1 electron. And chlorine is converted to a negative ion, chloride negative ion, because it is gaining an electron. Now between sodium positive and chlorine negative ion, there will be an electrostatic force of attraction, and it will bind the 2 ions together to form sodium chloride. You can see in this diagram. It's very clear in the diagram. You can see on the left hand side there is sodium, and the outermost orbit is containing a red colored, that is actually the electron. It is shifted from sodium to chlorine. So you can see in the right hand side, the red colored electron from sodium has come to chlorine. As a result, their electronic configurations are changing from 281 to 28, and 287 to 288. And at the same time, sodium is on the right hand side getting changed to sodium positive ion. Chlorine is getting converted to chloride negative ion. And between these two ions, the electrostatic force of attraction has kept them together to form sodium chloride or common salt. So this type of compound like sodium chloride, which are formed as a result of chemical reactions, are called as ionic compound or electrovalent compound. So what is an ionic compound? Ionic compound is that which is actually formed by the electrostatic force of attraction between the ions. Ions of metal and ions of non-metal, means the cations and anions, when are held together, then the compound which are formed are called as ionic compound. They are also called as electrovalent because electrostatic force of attraction held these ions together to make this compound. So sodium chloride, magnesium chloride, etc., all salts are ionic compound. Now, what are the properties of ionic compounds? The first property, ionic compounds are solid and hard due to strong electrostatic force of attraction between the positive and negative ions. You will see second thing, that they are generally brittle and break into pieces when pressure is applied. When they are hammered, they will break down into powder. Ionic compounds have very high melting points and high boiling points as considered to the amount of energy required to break the strong molecular attraction or ionic attraction present in these compounds. They are generally soluble in water, but they are insoluble in organic solvents like kerosene, petrol, diesel, mustard oil, etc. Ionic compounds in the solid state, they never conduct electricity. But if you can melt them, that is in their molten state, or if you can dissolve them in water in the form of their solution, they will conduct electricity. That is to say, the property of ionic compound, the fifth property of ionic compound is that ionic compounds are good conductors of electricity in their molten state or in the form of their solutions. Thank you very much.